Hi, thank you to organize for this opportunity to present this work here. This work is in collaboration with Abhishek Shikabalya, previous PhD student, and Kamila Kowalska and Eriko Sessolu at the National Center for Nuclear Research, who have a postdoc in Warsaw, Poland. So this work will soon be published on PRT. And today I'll talk about the neutrinos, dark matter in the context of UV completion of a standard model with gravity. And I would like to introduce this asymptotic state and quantum scale symmetry before we talk about how can we actually get neutrinos and dark matter in this framework. So as you well know, neutrinos, they are massless in the standard model, but due to the observation of neutrino oscillations, the neutrinos should have mass um, at least 2 out of 3. So some modification to the standard model needs to be done. Also, we know that if we try to apply the standard model of cosmology, we would need some dark component, dark energy and dark matter, a lot of them, but we don't know what is this dark matter, for instance. One can have gravitational origin, can also be a particle. There are many different models, WIMPs, new scales, axions, axion-like particles, and so on, but nobody detected. Today you see one more of them, one more proposal, but I would like to emphasize here, our work is not a final work, it's a theory work, and this idea that there is a new or at least an interesting way to um, do model building using quantum scale symmetry, this way I would like to emphasize today in this presentation. How can we get neutrino masses and dark matter using quantum scale symmetry? And the quantum scale symmetry or asymptotic safety can be used as synonyms here. What I mean is that from a given scale, can be the Planck scale or can be above the Planck scale, there is a moment where no longer how much you increase your energy scale, there's effectively no new scale. That's why quantum is scale symmetry. And the key idea is that there is quantum scale symmetry in nature. This is our fundamental assumption above Planck scale, trans-Planckian scales, in such a way that the gravity, the standard model, or beyond the standard model is UV completed. And is UV completed because your couplings, they will no longer run from this scale up to higher energies. So you will complete your theory of gravity, also your standard model beyond the standard model. We know that in the standard model there is U1, abelian gauge coupling, has a Landau pole. It's not UV complete by itself. You also know that gravity, general relativity is perturbative, not renormalizable. So this assumption of asymptotic safety is also a proposal of a quantum theory of gravity. The question is, can we then describe both things together, gravity and dark matter, neutrino? This is also what we would like to investigate in this framework. So here it's a dictionary so that it becomes clear what I mean later by interacting fixed point. Asymptotically safe requires that we have an interacting fixed point. This fixed point is not a zero, because if it is zero, then it's like asymptotic freedom, like QCD. It goes to zero at the high energies. This asymptotically free fixed point is also known as a Gaussian fixed point. And the non-Gaussian fixed points are the interacting fixed points. Well, if there is asymptotic safety in nature, then this means that we would need to have an interacting fixed point. This is the UV completion. But also we would need a finite number of free parameters because we need to fix these free parameters of experiments, and that's why we need a finite number of free parameters. This is the condition for asymptotic safety. Although the parameters, they are predictions, they can be infinite. How do we know whether these parameters, they are free parameters or if they are predictions? By the so-called critical exponents. These are basically minus the eigenvalues of this stability matrix here computed with the beta functions. And then this slide here, it helps to clarify why there are free parameters, why there are predictions, depending on the sign of these critical exponents. If they are free parameters, it means that their critical exponents are positive. These are so-called relevant directions, and they are UV attractive. You can see that if we start here at the deep UV from this fixed point and we flow from the vicinity of this fixed point to low energy scales, we can see that we can get very, very different trajectories. That's why it's infrared repulsive, but UV attractive. Now, if the sign of discrete correspond changes, the situation is different. There are different trajectories coming from different points at the UV that are being connected to the same point at the infrared. That's why infrared attractive, ultraviolet repulsive. These are irrelevant directions. These are the predictions because it doesn't matter from where we're coming from. We're finishing exactly on that point. That is a prediction of your theory. Now, let us then assume that this gravitational fixed point exists at trans-Planckian scales, can come from asymptotic state, quantum gravity. But let us assume that this is indeed a fundamental principle, a fundamental symmetry of nature, that there is this gravitational fixed point, there is quantum scale symmetry. And there is good evidence in the asymptotic safety community that this fixed point is there, but I will not go into details in this presentation. Rather, I will jump to the question, how can we put the matter to this gravity scenario? Well, and how does this gauge and the Yukawa couplings they run with gravity? It's actually an interesting question. Actually, this is a scheme-dependent answer, but the thing is that when we compute this contribution for the running of the gauge coupling, for instance, in asymptotically safe using functional normalization group techniques, we would get an expression like this. And the thing is that this the contribution that's linear to the same gauge coupling here, this can have the correct sign so that we induce gravity induce an interactive fixed point that without gravity is not there. So there is asymptotic safety for these gauge couplings. And for the Yukawa coupling is a little bit more uh, complicated, but also we can have situations where the sign of this contribution, linear contribution to the Yukawa running also has fixed points for the Yukawa sector. What's interesting here is that at least the order, these corrections, they are universal. For abelian, for SU2, for SU3, the value of G should be the same because gravity is blind to these symmetries. Gravity makes no distinction, so they are the same. But the value of this FG, that's why they are scheme dependent. That's why in our paper, in a couple of papers in the community, we treat this FG as free parameters. Then later you can have your theory of gravity, quantum gravity well developed, you can compute what is the value. But let us assume that they are free parameters, and for us we need a positive so that we have this fixed point, this induced interacting fixed points. And then the next question is this, can we explain neutrino masses and dark matter within this framework? There are already a couple of works that explore this question of neutrino masses and dark matter. And today you see at least a new aspect, at least two very interesting aspects of this search for neutrinos and dark matter within asymptotically saved. And the concrete example used is a model coming from Grand Unification. Well, this will help us to understand the new feature that we propose in our paper. Let's suppose you have a Lagrangian, the gauge that is gauge invariant. Let us take a look at the Yukawa sector. So all these terms here, they are invariant under this SU6. That is the symmetry here. They are all allowed by the symmetry. Well, but for instance, if you try to get dark matter out of it, there are so many couplings that this is probably leading to decays, and this cannot be dark matter. That's why usually people have to introduce global or discrete symmetries to forbid couplings that hinder you to get the dark matter with this model. And this is what most works in the literature does. So what is interesting is that actually, if we use quantum scale symmetry, we can have a secluded mechanism that instead of imposing ad hoc these global discrete symmetries like SE2 to forbid decouplings, the quantum scale symmetry itself, through the fixed point instruction and the RG flow of these couplings itself, we get rid of this undesired couplings mixings. And that is the feature we're mostly advocating in our paper. That's why it's stabilizing dark matter using quantum scale symmetry. But also, of course, we also have neutrinos here, and that's the second aspect I would like to emphasize a bit later. So let us first understand how this model works. It's coming from SU6. It's nice that in GUTS the gauge couplings are unified above the GUT scale, should be around 10 to the 16 at least to avoid problems with proton decay. And then if you try to search the most minimal scenario, you can come up with this anomaly-free fermi content. So there are three copies, identical copies with this fermion contact. The standard model will be inside here, but also there is dark sector, and from there we will try to get the massive neutrinos and the stable dark matter candidates. There's also scalar content that needs to give mass to all of these guys. In our work, we focus on the further generation. Later we can comment more what should we do with the other generations, but let us focus on the further generation. Very briefly, this is the scalar sector after the symmetries are broken to the electroweak symmetry breaking scale. It's like a two-Higgs doublet model, but we give vevs for both doublets, so no dark matter is coming from the scalar sector. But there are also two complex singlets that break this extra U1 symmetry that comes from the breaking of SU6, and that therefore also have a Z prime in our model. So we have the spectrum here, but we want neutrinos, we want dark matter, we focus then in the Yukawa sector. This is the Lagrangian at the electroweak symmetry breaking scale. And for each generation, we have 5 neutral massive Majorana firms. So this is the mass matrix. It's here. The spectrum contains a standard model. You give mass for the neutrino, and also have fermions here, including for each generation, heavy neutrinos. The lightest of them should be the dark matter one. The thing is that there are so many couplings here, like I was telling before, that there will be no stable dark matter candidate. And this is the problem. How can we, in such a difficult model, get dark matter? Well, the solution is to use quantum scale symmetry. We have our beta functions for the gauge couplings, for the Yukawa couplings. You have the gravity contribution parameterized here by Fg and Fy. And then the idea is that we have this full system that there are many fixed point solutions, but we will select a fixed point solution that has these properties here. And it turns out to be the most predictive solution that is compatible to phenomenology. But what's interesting here is that we have a bunch of Gaussian fixed points here. Some of them, they have positive critical exponents, so they are free parameters, but some of them, they have negative critical exponents. If you remember, let us remember, if they have free parameters, they can, even though they start at a 0, at the UV, they can give you different values at the infrared that are not a 0. So you can use this free parameter to match something with the standard model, for instance. They are not predictions, but they are possible, they are allowed. On the other hand, if they are irrelevant directions, if they are predictions, and if the fixed point is 0, then you are in the situation of this green line here. It stays 0 all along the flow. And this thing, to stay 0 all along the flow, this is the thing that you stabilize the dark matter. Well, now if you still have critical exponents that are negative, but now your fixed point is no longer at a 0, then you can have non-zero predictions at the electroweak symmetry breaking. And for instance, you can use this to get the top and other P under standard model masses. So this is how we turn off a lot of couplings. And from that difficult Lagrangian, we get a very, much more simple Lagrangian that's here. We have top, we have predictions, we have free parameters that match the standard model, will be used to match the standard model, and you have dark matter and neutrinos predictions of the theory. So this is what we need to get a stable dark matter. And also good standard model particles. Well, the thing that we need to pay attention here is that because we turn off so many couplings here, is that now we made the neutrino become massless. So this can only happen for inverted order because we are using the third generation, are using the top to fix things here. the two other generations, they must have a different fixed point structure. That is the trivial one, Gaussian fixed points that are relevant so that we can get something that's not a zero. But let's focus on the first generation. How can we get some mass for this neutrino? Actually, it's very interesting work that Kamila Kowalski, Enrico Sessolo, and Pramanik, they were working some years ago. The idea is that you'll be able to turn on very small couplings dynamically without fine tuning. So if you think about the previous fixed point that we were analyzing before, this should be equivalent to this fixed point F. It is zero for the neutrino, but not zero for the top. The thing is that if you already sit at this fixed point at the deep UV, then this Yukawa coupling for the neutrino is zero, and it will be zero all along the flow when gravity is turned off from the Planck scale to the electroweak symmetry breaking, and the neutrino is massless. But now we also have a different fixed point in our model, that is this fixed point E, that is Gaussian fixed point. But it allows us to start from this fixed point E at the deep UV and flow towards this attractor F here. And depending on the trajectory that we choose, we can get different masses for the neutrino. And this is one example here in our paper. This tilde 1 controls the mass of the neutrino. See that we can have very small couplings with this guy. Basically, the infrared value depends on the choice of trajectory, which trajectory we choose from the UV to the infrared. And here we can see, depending on how quick comes this effective Planck scale here, we have different values for the Yukawa couplings of the neutrino. This means neutrino we can choose the trajectory that is selected by nature. There is no fine tune. All these trajectories are allowed by the theory. Nature selects only one, and this is this would be the mass of the neutrino. Well, so this solves the problem of giving mass to the neutrino. So in our model, we have two possibilities. First possibility, the most predictive one, yeah, the lightest neutrino is massless, and we have two dark matter components because the sector is also secluded. Then there are two dark matter components, and we have inverted order for neutrinos. If then we use naturally small Yukawa couplings, this mechanism that I explained before that can explain small masses for the neutrinos, then now the neutrinos are massive, and we also we can induce, like in this plots here, by tide 1 and tide 2 the decays of one of these dark matter components. So it's no longer two dark matter components, but now a single dark matter. It can be a singlet on the left or a Higgsino-like N2 and 3, the doublet, the candidate of dark matter. And that's have a rich phenomenology, and that's the thing that we are actually working now at this moment, how to get these dark matter predictions. At least at the analytical level, we were able to get these constraints on relevant parameters here on the Z prime as a function of the mass of the dark matter. We can actually put upper bounds for the Z prime, either with the singlet case or with the Higgsino-like case. Yeah, so this is pretty much what I'd like to talk. There's asymptotic safety, there's quantum symmetry. The asymptotic safety is a UV completion of gravity with matter interactions. And we use this quantum scale symmetry as a way to forbid couplings. Couplings that they will be there, they will spoil, for instance, the stability of dark matter. And instead of introducing ad hoc discrete or global symmetries, quantum scale symmetry itself forbids these couplings. And we also saw that neutrino physics is possible. In the most predictive scenario, though, the lightest neutrino is massless, and we have a two-component dark matter. But if you use this naturally small Yukawa couplings mechanism, also within the scope of quantum scale symmetry, the presence of two fixed points, all of the neutrinos become massive, and dark matter is now a single component. What we're doing now is to work out the phenomenology, numerically, the viability of this model. And this is the work in progress. Thank you for this opportunity to present this work here.